Good afternoon, everybody. So today we are joined by Tjarda Roberts, a research scientist at CNRS, French National Centre for Scientific Research. So Tjarda obtained her PhD in atmospheric chemistry from the University of Cambridge in 2009 and undertook her postdoctoral research at the Norwegian Polar Institute and a guest lectureship at the University Centre in Svalbard before becoming a CNRS research scientist in 2016. During today's webinar, Tjarda will discuss the opportunities and challenges around using low-cost, small sensors to measure air pollution. As always, there'll be a chance as attendees to ask questions at the end of her presentation, so do please submit these at any point during her presentation using the Q&A function at the bottom of your screen. That should be visible to you now, and I will then ask these on your behalf later on. So thank you all for logging in. I'll now hand over to you, Tjarda.
Thanks very much. And thanks everyone for coming. So, as Rena said, I'm Tjarda Roberts. I'm a CNRS researcher here in Orléans in France. But I did my PhD at the University of Cambridge in the UK, and that's really where I started looking at small sensors, low-cost sensors for measuring air pollution. And my background was using these sensors to measure gases and particles coming from volcanoes, so really at very high concentrations and emissions of hundreds of ppm. And then during this last year, I've been working more towards using the sensors to measure lower levels of air pollution in urban environments, and actually moving to another extreme kind of environment, which is Arctic air pollution in Fairbanks, Alaska. So I'm going to talk to you today about those measurements in Fairbanks and what I've learned so far and what I'm still doing. It's still very much an ongoing analysis, so I'm really interested to hear your thoughts as well from this webinar. So, I'm first going to start talking a bit about some motivation and give a bit of an overview before I talk about measurements both in the gas side and the particle side from low-cost sensors. So the main motivation is, can low-cost sensors help to quantify urban air pollution, and what are the issues that need to be overcome, especially for the Arctic in these very cold environments where temperatures can get as low as -40. That was also the other reason for wanting to go to Fairbanks, Alaska, is because during wintertime they observe air quality episodes that are really severe. So sometimes Fairbanks, Alaska is the most polluted city in the whole of the US. And there's a really big international effort ongoing right now called ALPACA, Alaskan Layered Pollution and Chemical Analysis, where we're trying to think more about what is the processes, the chemistry and the meteorological processes behind these air quality pollution events. So as part of a kind of pre-ALPACA campaign in 2019, there was a French-US team in Fairbanks deploying a whole host of different instruments in order to try and quantify and understand and characterize the pollution better. So I'm going to talk to you about those results today. You can see there's some web links if you're interested more on these collective goals. So my goal is really to evaluate these small low-cost sensors in comparison to other instruments. And this is a picture of our measurement site. So I was deploying two kinds of low-cost sensors. One is this purple air, which is a low-cost sensor for instrument for particles. And I also deployed two Praxis instruments, which are instruments containing low-cost sensors for both particles and gases. This is the roof of our trailer. So we had an inlet here that was bringing in air to instruments inside the trailer. And you can see at the bottom here, there's the purple air, the Praxis, as a close-up here are the sensors. Within the trailer, we had some more sophisticated instruments held at room temperature, including an SMPS for particle size distributions. And next door to the trailer was the DEC Alaskan air quality monitoring site called Encore, which hosts a whole range of other instruments, including BAM for PM 2.5 and various gas monitors. So I'm going to just talk through now, describe the different sensors. So first of all, this is the purple air instrument, which is measuring particles. It contains a Plantower OPC, or two, in fact, inside each instrument to measure PM 2.5. It also reports other PM. and at a resolution of about 2 minutes, and you connect it via Wi-Fi upload to a kind of cloud, and it's also optional to store the data on SD card. But then once you've done that, the data is then coming online automatically and is open source. So you can see the data from purple air instruments all around the world in this map. And right now, of course, we have a lot of pollution in the west of the US due to the wildfires. So you can see that coming up nicely on this figure. So that's the purple air. And I also deployed 2 Praxis instruments from South Coast Science. So these are measuring both particles and gases. Again, the PM 2.5, another PM, as well as counts in 24 size bins, and 4 gases with electrochemical sensor. So in this study, we chose CO, NO, NO2, and OX, which is a measure of ozone and NO2. And you can see an image of the alpha sensor, electrochemical gas sensor here, as well as the particle sensor that are contained within the Praxis instrument and hosted within it. If you're interested in more information on these sensors, as well as some low-cost sensor applications generally, there's a very nice review by Baron Safel in Sensors that can explain more details. The resolution of the Praxis is a bit higher, it's at 10 seconds, and there's also a GPS location of where the instrument is located, so it tracks where you move it. And we operated it with SIM card upload, so the data was coming via SIM card direct to the South Coast Science Cloud, and here's some examples of sort of live stream data that comes straight through every 10 seconds, resolution data coming through on their site. The Praxis stores both the raw data and some process data with some automated algorithms to give you a direct result. This is also the same for the purple air. You get raw data and sort of a processed PM result, for example. So then alongside that, we were deploying some more traditional standard instruments for air quality. First, I want to highlight the Encore air quality monitoring site. And this is really thanks to a great collaboration with the Alaskan DEC, who provided some provisional high resolution data to us from their air quality site, including PM 2.5, as well as CO, NO, and ozone for comparing to the small sensors. And we deployed ourselves in an intensive field campaign in November to December 2019, a host of different instruments, including SMPS, which gives size resolved particles up to 700 nanometers, and also a suite of small sensors, which are the same alpha sensors deployed in the Praxis, but here they were being deployed with a pump and sort of an inlet to outside, and the sensors were held at room temperature. Whereas in the Praxis, it's outside, so it's obviously at ambient temperatures, which in the Arctic can be pretty chilly. So it was exciting to see how these sensors would perform. And I'm just going to go through now and give you a bit of an overview of the field campaign, November, December. So we observed different pollution regimes and meteorology regimes. So we actually sort of can identify 3 periods. In the beginning, it was kind of warm, and then the temperature descended down to nearly -30. And then afterwards, a warmer period again. And you see there was an inverse relationship with the pressure, ambient pressure. And at this time, you can also see that the particles also increased a lot during the very cold period, and were also pretty high and polluted just after that very cold period. But when you look at this time series here, in comparison to the full winter season, so this is provisional data again from the DEC, you can see this period that we were observing in late November, early December was actually just the start of the season, and it got a lot more polluted later, as is quite common in January and February, when temperatures really became very cold and it became very stable. But nevertheless, I think it was a very valuable campaign to identify some of the processes going on and also test out the sensors. Yeah, as I mentioned, we had these sort of 3 different regimes, and our ongoing work is to really understand the meteorology, the chemistry, the emissions, and the vertical mixing that are behind the air quality patterns and tendencies that you tend to see during winter. So And just now to give you already sort of the answer of all the conclusions of this talk, which is the take-home point about the low-cost sensors, which is what we find is that they can deliver very good quantitative air quality measurements of both gases and particulate matter, provided that the sensors are well characterized. So, and this is a result that other groups have also been finding, I'd say, that in each different location, you need to sort of think about the conditions and characterize your sensors well. But here in this Arctic application, going to very low temperatures, we got pretty good agreements both for particle time series, which is along the bottom here, and gases, for example, CO along the bottom here. So what I'm going to do next is to talk a little bit more about the details of the analysis, ongoing analysis behind these sensor observations. And this is it's a work in progress, but in a way it's kind of quite interesting to actually see what's going on step by step behind the results that eventually then get published. So here I'm going to talk about the results in two parts, basically. In part one, I'll talk about the gas measurements from the low-cost sensor. So this is from about the Praxis. So the data is coming out at 10 seconds resolution, but we're averaging it to 5 minutes in order to compare to the air quality monitors that were co-located. So here you can see time series for NO2 and CO, so nitrogen oxide and carbon monoxide, and in black is the time series of the air quality monitor, and in purple and orange are the two Praxis that are essentially identical instruments, and this is really straight from the instrument, the automated algorithms that basically take the sensor output, they apply some kind of function, usually in terms of temperature, and they give an estimate of the mixing ratio of the gases that's observed in ppb or ppm. So you can see that these automated algorithms are giving very good variability that's co-varying with the observations, but there's a bit of an offset. So one of the first things I did is just to do a kind of simple baseline and sensitivity shift, like a Y cosine X plus C, just a simple shift, just to, I mean, it's quite common to do that with a lot of instruments, not just low-cost sensors, but to see really how good the comparison is. And you can see it's pretty good for the NO2, where it's giving a very good agreement. For the CO, also a very good agreement, except this period, just very late November, early December. And actually, given that both the Praxis CO sensors are suggesting that CO is higher, and that this sort of step down to lower CO probably seems a bit unusual. We actually think that this is probably just a correction that needs to be made to the CO monitor, the air quality monitor, from the data that we had, which was provisional at the time. So they usually do an air quality check later, a quality control check later on their data, and we'll discuss with the DEC that further. But we think this is probably more likely the true air quality monitor result. So it's pretty good, but I can also see that during this period in early December, which was actually the coldest part of the field campaign, we are underestimating slightly with both sensors. So I was then motivated to try and see if we could improve that, because we'd like to be able to measure accurately during the real coldest periods. And so I then also created some sort of user improved algorithms specific to the sensors and to the conditions, which are still just simply a function of the sensor output and the temperature. So I should mention this is temperature co-measured within the Praxis instrument. They deliver a temperature out of the actual sensors. But yeah, it's possible to create functions that can maybe be more accurate under certain conditions. This one is using raw data, but another way would be to sort of do a correction based on the Praxis output itself. And it kind of brings the readings with this cold temperature up a little bit and could be slightly more accurate for those conditions. And just to explain sort of it was inspired partly by looking at the data and looking at realizing that, you know, there is a slight bias during certain temperature periods, and partly from also looking at the data sheets from Alphasense, who are the manufacturers of the sensors, and they provide a lot of really useful information on things like temperature dependence. You need to consider the sensitivity, but also the baseline of the sensors. Yeah, so doing that then gives a pretty good agreement. I have not gone into detail yet, and really high level detail on the analysis of this, but the scatter plots of from the AQ monitor and from the Praxis for both CO and NO2 show pretty good correlations and sort of nice agreements. A little more scatter in the CO than the NO2 in this case. Yeah, and I guess what's also remarkable is we are at very, very high pollution levels here, even during this sort of mild pollution episode that we observed during our campaign. And this also can be seen in the NO and the ozone sensor observations. So this is, again, this is the algorithms, automated algorithms. So these are straight from, delivered from the Praxis without any tuning whatsoever. So you can see for NO, one of the Praxis is giving very good agreements. The other one has a bit of a sensor baseline drift, which is probably related to temperature again, and I will look into improving the correction for that. But it's still capturing the variability pretty well. And NO levels are super high, up to 100 ppb. So it's not surprising that ozone is getting titrated with so much NOx around. So on the right here, you can see the time series for ozone, and you have some ozone that's being, when ozone is present, it's measured very well by the sensors. When ozone is basically zero, it's kind of harder for the sensors to get it exactly right, and that's just actually probably due to the treatment of the interference, because you're actually measuring OX, ozone and NO2, and then subtracting NO2 from the NO2 sensor. So you're putting a subtraction in the equations will make your errors get bigger, basically. But I think these are things that we can still work on in a similar way to, as I just showed for CO and NO2, and hopeful to get even better results than this through doing further analysis, even though I think they're pretty good already as a first look automated product. And actually, one of the approaches we're doing is an ongoing work is to compare these Praxis results with some small sensors that were deployed inside at room temperature in the heated trailer. So these are the same AlphaSense sensors, but deployed in a different way with a pumped flow system to outside. The color scheme is different here. So the AQ monitor is in yellow, but you can see here on the bottom left for NO time series, it's capturing very well, and even with fewer biases, the NO probably in this case. And for ozone, also similarly, do a very good capturing of the peaks. And then again, still having this issue at low ozone when there's actually no ozone, that this is where you start to really see these errors of your baselines not being 100% right. But I think that's something we're working on, and I think can be corrected further. In ongoing work. But yeah, I think this approach of looking at the temperatures at the sensors at ambient temperature and inside can be really fruitful in that sense. So yeah, that's basically firstly what I wanted to say about the gas sensors. And then now I'm going to talk a bit about the PM measurements from the instruments. So the Praxis had 4 gas sensors and also an AlphaSense OPC within it, optical particle counter. The purple air is no gases, but includes this sort of OPC or particle sensor for PM 2.5. And then, so we're operating these 2 outside the trailer. And then within the trailer, we operated an SMPS for size resolved measurements. And there's also the BAM from the DEC air quality site next door that is giving PM 2.5. But before we can really sort of go into detail at thinking about the data, I just wanted to put out a kind of disclaimer. So this is provisional analysis, and for the moment, I'm not correcting for any differences in sensor temperature, humidity, or the assumed particle densities used in the analysis from the different instruments. And whilst there are very big differences in the temperature and humidity of the different sensors due to their operating conditions, I think the overall findings are still quite valid as a first look, and doing the corrections for the for example, for the fact that the particle measurements are at different relative humidities is something that's ongoing. But just to take you through it, here on the top is temperature. So the ambient temperature in black is the coldest, going down to nearly -30 in early December. The two purple air instruments are, they're quite small sensors, so they don't have very much internal heating, but just a little bit of a few degrees. The Praxis is a bigger instrument with more sensors inside it and a bigger particle sensor. So there is more internal heating. So you have a 10 degrees or so difference in the temperature of the actual OPC sensor within this instrument. Yeah, I should point out, so here this is temperature from the OPC. The Praxis is also delivering a temperature specific to the gas sensors. So it's actually, yeah, the temperatures, it's important to use the right temperature from the right sensor to get the best corrections in the analysis. And then finally, the temperature within the trailer itself is shown in red and is around 20 degrees, varying a bit depending on how well we were heating and keeping the temperature up. So yeah, you can see that generally relative humidity was lower during this cold spell, ambient relative humidity, and that's also reflected in the instruments, but also the relative humidity of the purple air versus the Praxis is reflecting the actual temperatures of those, or inversely reflecting the actual temperatures of those sensors. And then I just wanted to add for the Praxis OPC, we actually put some insulation around it at one point, well, for quite one of them, for quite a large part of the campaign, because we weren't quite sure how well they would withstand sort of Arctic temperatures, but although it turned out they withstood it very well, even down to -40. But because of adding this insulation, you can see there is a slight jump in the temperatures and also in the relative humidities of these two normally identical instruments. And in the periods where we didn't have the insulation, the temperature and humidities are basically the same. So that's why there is this offset for the middle period here. So yeah, just wanted to point that out before going on to looking at the data. So this is PM 2.5, and now we're looking at 1 hour averages of data in order to be able to compare to the BAM, or the beta attenuation monitor from the DEC air quality monitoring site. So that's shown in black in these two figures in the time series. And then the two purple air instruments contain altogether 4 sensors. So I'm comparing to the PM 2.5 in this top, from the purple air in this top plot here. And on the bottom plot, I'm comparing the two Praxis OPC PM 2.5 from those two instruments. So you can see overall we have a pretty good comparison. You're kind of capturing, especially the purple airs are capturing very well the kind of clean period and the small pollution events during the clean period, then the cold and polluted period, and then also the warm and polluted period just afterwards. It's also captured by the Praxis, although a bit less well in the cleanest of the period. There's a slight offset between the two sensors here, and the correlation maybe seems a little bit less good. So if we look at the correlation plots, on the top here you see the one for, so it's the purple air PM 2.5 versus the BAM PM 2.5. You see a very good correlation. You also see a very good correlation for the Praxis PM 2.5 and the BAM PM 2.5, but a general slight underestimate and a slight difference in the sensors. It's probably a small calibration issue. But actually hidden within this, what looks a good result in the purple air is also the fact that actually there is a temperature bias. So I've plotted here in triangles the temperature of the very cold data below -20, and in circles the temperature when it, the results when the temperature was above -20, and you can see actually there is a tendency for the purple air to read quite low and be low biased during these very cold periods. And we think this might be due to a slower flow rate when it gets really cold in those sensors. Conversely, the OPC, our sense OPC within the Praxis instrument actually includes a flow rate monitoring and its own sort of compensation for any flow rate changes. So we're able to look at that data, and we saw that the flow rate slowed by about a factor of 3 or 3.5 during the coldest spell, but that the Praxis is itself compensating for this slower flow rate in the observations that the OPC is making. So, so that's those data, but there is another issue to think about, which is actually OPC, so optical particle counters, have, as hosted in both the Purple Air and the Praxis instruments, do have a detection threshold that's typically around 0.3 or 0.35 micrometers diameter. So it's possible, and quite common actually, that much of the mass could be in particles that are too small to detect by these low-cost sensors, or even by any OPC sensor. And it does lead to the question, well, how well would you actually expect the PM 2.5 from such a sensor to compare to the PM 2.5 from the BAM, which is a full PM 2.5 measurement over all sizes, up to 2.5 microns. So a way to think about this was to actually, it's possible to calculate PM in the diameter range from 0.3 or 0.35 to 2.5 micrometers, basically using the data observed, measured by the BAM instrument, and calculating the relevant parameters from the SNPS and doing a subtraction to get particulate matter in this sort of size fraction, which is the fraction that corresponds to the OPC measurement. So that's what I'm going to show you now. So you see here, this is the original data, PM 2.5, 1 hour averages for the Praxis. And then now, this is this PM on the same scales, PM 0.35 to 2.5, as I call it, still 1 hour averages. And actually, you see, if I just go back, this is the PM 2.5, and then this is the PM 0.35 to 2.5. The agreement is really very, very good now in the size range which the sensor is measuring. So this above 0.35 range. And so you can see really nice capturing of the sort of more particles of this size during the cold spell, and also a bit during the polluted part when it was a bit warmer just afterwards. And you can see this reflects also nicely in the scatter plot that is now sort of doesn't have those biases that seemed to have before. So it does open the question, what's happening in the Purple Air? Why? Because this is not really possible to do this analysis with the Purple Air and get the same result, and I'm not yet sure about that. There may be some sort of scaling to deliver an estimated general PM 2.5 or something with that instrument, perhaps. That's just a speculation, but we'll probably talk to them and see. But given that this data from the Praxis was actually looking really quite promising in terms of the size distribution, and also the fact that there aren't any obvious temperature biases at all. There's a slight offset from one sensor to the other, but there is no temperature biases within the data. I thought it was then quite useful to look at the size distributions particularly in the cold polluted period and the warm polluted period, and see what the instruments show. So here is the particle size distributions during those periods as measured by the SNPS, so very small sizes, up to 700 nanometers. And you can see that you do see some differences. You can see that there's a lot of mass in these small sizes. And the cold polluted period, the maximum of these curves, which are dV by d log d versus diameter. So the sort of the area under the curve tells you about total volume and therefore total mass. But you can see that the maximum is a bit higher for the cold polluted period than the warm polluted period, and is reached a bit earlier, perhaps, during the warm polluted period, actually, compared to the cold one. And this is still sort of analysis ongoing, but here is data for the same, from one of the Praxis for these same 2 periods of time. And you can see it's like all the data and then the mean shown in black. You can see that the Praxis is confirming that there seems to be a lot of particle of particles in this mass in the very small sizes. And in fact, the PM 2.5 measurement is just capturing the tail end of the size distribution. So it's really in these smallest size bins, kind of below 1 micrometer, where there is really a signal that seems to be fairly consistent with the SNPS, at least in a general sense. I should emphasize again that there's for the moment, no temperature or humidity corrections, and also the density assumed by the analyses of the different instruments can be different. So this is really just a quick look. But it just seemed to show we see a nice difference between the cold and warm polluted period in terms of what is how far the size distribution is going up and how it goes down with size. And so this gives sort of a promising indication that we might have a little bit of information also on the size distribution from the Praxis here. And for particles above 1 micrometer in Fairbanks, Alaska during winter time, I'm not sure how much information there really is, because it does seem that the most of the information about PM and the PM 2.5 is really at these lower sizes that are just captured by the optical particle counters, and the rest of the distribution is being captured by the SNPS. So I'm nearly coming close towards the end now. I didn't have this summary slide, which is just sort of summarizing what I've found so far with analysis of these sensors in the Arctic, both the Praxis and the Purple Air instruments. They operated very well down to -30 or even -40 degrees C, and it was very helpful to have deployed multiple instruments at the same time of the low-cost sensors and alongside the air quality monitors to really be able to cross-compare and cross-calibrate. There are some big issues in terms of needing to think about sensor baseline or sensitivity to get the best results, and the algorithms, automated algorithms, so you need to measure temperature and humidity alongside, and this is done in the Praxis and also Purple Air, but in the Praxis for the gases and the particles at the locations of those sensors. Yeah, then it's possible to either just use the raw data, use the process data, the automated algorithms that have include these temperature corrections from these sensors, and they give pretty good results. So you can do some minor offset adjustments in capturing both the gas and particle trends. But I think it's also really neat that both of these instruments deliver also the raw data. So it means as a sort of end user, I can play around a bit either with the process data or the raw data and try to include new ideas on the temperature corrections for the specific sensors in the specific conditions, because it may change from one location to another exactly how some of these sensors are performing. So this is my very last slide. I'm gonna stop here. If I've got one final minute, I'd love to just talk a little bit about what I'm going to do. So we're now with our sort of French CNRS and with the University of Alaska team, we're in the process of trying to characterize these different air quality regimes we observed and elucidate the causes behind them in terms of emissions, chemistry, meteorology and mixing, and also to further optimize the small sensor analysis algorithms, and so we can characterize the pollution in relation to boundary layer. And actually what I did after this campaign, this 3-week campaign in last November, is I left the 2 Praxis with Bill Simpson at the University of Alaska, and along with his student Mita, they did a really nice study deploying those sensors alongside other instruments throughout the whole winter. So the Praxis were installed on this trailer with a 10-meter mast that was then essentially running at different locations around Fairbanks throughout the whole winter to see if we can observe emission composition or how the emissions vary in different locations depending on traffic or home heating, for example. And Mita did a very nice study here with 2 Purple Air sensors. One is deployed at ground level, or on this trailer essentially at the ground, and one was actually deployed on a roof of a building at 20 meters above ground level. And by comparing these 2 sensors throughout the whole winter season, she could look at the fact that you do tend to see more PM 2.5 as you'd expect at ground level compared to the sensor on 20 meters, but also using the data from the mast, the 10-meter mast at different levels, she was able to look at temperature difference as a measure of inversions and can see how PM 2.5 at ground level really becomes very enhanced during the extreme inversions observed when you know, these very cold conditions, and it gets down to -40 and all the pollution gets trapped in the bottom layer. So yeah, that's all I wanted to say today, and thank you very much for listening, and I'm open to hear your questions.
Thank you, that was brilliant, really informative, thank you. We have got a couple of questions that have come in, so I want to utilise the time. One has asked, what system do you recommend for real-time particulate monitoring on construction sites where it must be solar powered?
Well, I think both the Praxis and the Purple Air, they're the two I've tested, would be good in that sort of location. It depends also, so the Purple Air, it depends on how you want to look at the data, if you want to have it in real time or not. The Purple Air is with a Wi-Fi connection only, or with a card that you'd have to physically sort of retrieve, and you've no way of knowing if the instrument is not, if there's been a power cut or something. But the Praxis has the, can use upload via SIM, or it'll also log into an SD card. And I think a lot of the power usage actually, it's not very, I can't remember the exact figures, but the power consumption is really not very high in either of these instruments. So you can operate them on a lower power setup with having less data transfer, for example, but even a higher power one, both of them would work. I think it depends on what size of particles you expect to measure. Maybe a distinction between the two instruments, at least that's having a hint of that from Fairbanks.
Okay, perfect. That leads me on nicely to the next question, actually. So one of our attendees is considering an industrial application for these sensors, but the range of measurement would be in micrograms per cubic meter. Would the sensors cope with that? Would they be able to monitor that?
Yeah. So yeah, so you're talking about several orders of magnitude higher. It depends on the size of the particles. I think, so I have actually tested the AlphaSense OPC N3, which is the sensor inside the Praxis, at a volcano. So going into plume, which was very gassy and you can hardly see anything. And it seemed to be performing relatively well. I haven't finished analysing that data, but it certainly held up to the conditions. The big issue with trying to measure if it's many particles and many large particles is you can have sort of non-quantitative counting. There's too many particles go past the sensor in one go. So, so they're not counted individually, or two might be counted as one big one, for example. So certain sensors are better at dealing with that than others. What I found in the volcanic plume, having tested a French particle OPC from our lab and the AlphaSense OPC, is that the AlphaSense OPC was better in the very polluted conditions. The Purple Air likewise might be pretty good. I haven't done a full test yet on that.
Okay, brilliant, thank you. And someone's just asking about some of the larger problems that you observe when you use these sensors in relation to their sensitivity or deviation of the data compared to an FRM or FEM, and the calibration of these sensors. Have you got any experience or tips that you could share?
So I think the most important thing in urban environments is that you're at quite relatively low concentrations compared to the volcanic work I've done before. So knowing about sensitivity of the baseline as well as the sensitivity sort of response to the gases, so the baseline drift and the sensitivity. So those are two things that are both important, and they become really critical the lower you go in concentration. I think measuring with an air quality monitor nearby is really important to have this sort of cross-validation. You can do it through laboratory work as well, but in some ways, at least if you measure with air quality sensors nearby, you know the exact conditions where you're doing the comparison are the ones of the field measurements. I think there is some nice work going on with some groups, and this could be really valuable approaches. Obviously, you don't want to just measure at your air quality site because that's not adding any value. But if you measure these sensors at different locations, deploy them at different locations, would be to have one wandering sensor that you will co-deploy at the different locations, and that way you can get a sort of cross comparison that gives you an idea of the consistency of how all the sensors are performing within your network. That's probably the approach I would take. But yeah, this is something I'm going to be thinking about for analysing this entire winter series of Praxis data. But deploying two sensors also for periods is really, or two instruments is really useful to understand the variations.
Thank you. Another attendee's asked, are the sensors commercially available? And if so, do you have a rough idea of how much they are per unit?
Yeah, so I think I put the websites in from South Coast Science and from Purple Air earlier on at the very beginning in the methods. So these are commercially available instruments, and if you go on those websites, you can get information about buying them. I think the Purple Air is of the order of a few hundreds of euros, and the Praxis that contains gas sensors, 4 gas sensors as well as particle sensor, is a bit more expensive, of the order of a few thousand. But yeah, things are changing. It's a very rapidly moving field in terms of new products coming online and new sort of developments and innovations in what sensors are and what kinds of instruments are being developed, either ground-based ones like or sort of stationary designed instruments that are designed to be stationary, such as the ones shown here, or ones that can be handheld and lighter and contain fewer sensors. So the best advice is to go onto the websites for those two companies.
Perfect, thank you. And one's just seeking a little bit more clarification around your definition of warm and cold weather that you used earlier on. Could you just give your parameters or a bit more?
Yeah, so it was kind of, for the moment, this is ongoing analysis, so it was a bit sort of more just identifying 3 regimes. One is where it was not very polluted, one is where it was cold, and then that was when the temperature was decreasing at a very still condition. It went down to -30. And then the other was after that, where the temperature was getting around -2 or 0. And we were very surprised during that time that at the time that the pollution levels remained so high. But there could be various reasons for that. There was still a strong inversion, or reasonably strong inversion during that warmer period, which yeah was interesting, and you still had the emissions coming as well. So for this analysis I just presented, I more sort of separated the period and call it loosely warm polluted or cold polluted, but yeah, we'll be sort of defining more rigorously exactly with times essentially which of those periods are. But they're time slots rather than separating data points according to temperature.
Sure, okay, I appreciate that, thank you. And just to ask, can these sensors be deployed at city scale to contribute to networks such as London Breathe? And do they have the ability to transmit data in real time to the public via an API?
Yes, well, I think they are certainly can be deployed on in networks on a whole scale. I'm not familiar with the London Breathe one, but I will look it up. And they are just transmitting in real time. In terms of transmitting to the public, so the Purple Air is the data goes on to a sort of community website where you can see all the data from all the sensors that have been uploaded, provided they have Wi-Fi connection. And for the Praxis, it goes on to a sort of live stream website. But I believe they're also developing sort of handheld versions that can go straight to a mobile phone or something like that. I'm not actually sure what, confess my ignorance, what's an API?
I'm unable to answer that too. If
Okay.
The attendee, if you just
can tell me
what
an API is, then
yeah,
I'll be very pleased to hear it.
The chat box as well.
But yeah, I hope I've managed to answer your question more or less.
Brilliant. Thank you. We are just about to run out of time, so I'm going to have to leave it there, I'm afraid. Tjarda's details are on the screen, so if you have a burning question that you want to put to her, I'm sure she won't mind you contacting her via her email address, which is on there for you now. But just to say thank you to everybody who logged in. If you are an IES or an IAQM member, you can record this as CPD using the CPD tool. So just log into the members area on the website and you can record this. This webinar has been recorded and will be shared on the IAQM website and the YouTube channel for the IES. So do follow this. I recommend you subscribing, and then you'll be notified every time it's added. But that will be with you in the next couple of days so that you can use it as a learning resource. So the next IAQM webinar will actually be on the 13th of October, looking at reducing emissions from road transport, the journey to a net zero future. So further details on how you can register can be found on the IES and the IAQM website, and that is open to all IAQM members for free. So thank you all for listening. I hope you've really enjoyed that, and thank you to Tjarda for your time and for presenting today. It's been brilliant to have you on board.
Thanks very much.
Thank you.